The next problem we're going to do for review is one of, again, kinematics, and this time of analyzing graphs and connecting graphs of position and time with physical scenarios or physical setups. This is a good conceptual practice, and it's a pretty common kind of reasoning thing we need to be able to do for the AP exam. And in this question, students are using nearly frictionless cart and a dynamics track, a motion detector, and a LabQuest tablet to create position versus time graphs depicting the cart's motion. Which of the following graphs correspond to the given equipment setup? So first I will draw 4 or 5, I believe 5 graphs there above my green line. We're going to assume that away from the motion detector is going to be the positive direction, and so you'll see once I draw up my equipment setups, there they are going to be down below the graphs. I have some equipment setups that show the cart in purple. I have a green thing there, that's the motion detector. We said away from the motion detector is going to be positive, and I have black arrows that indicate the initial velocity of the cart, whether it was pushed or just being released and gravity is accelerating it downward. And then the golden arrows indicate the acceleration. I've numbered my graphs 1 through 5. I'm going to letter my equipment setups A through B, C, D, E. And I'm also going to put on there the positive and negative directions to help me remember which way is positive and which way is negative. You said in the problem that away from the detector is going to be the positive direction. So when I go to solve this, I need to look at both my graphs and my equipment setups and see which ones match. I've just kind of organized them randomly, the graphs above and the equipment setups below, so we need to go through and figure out which one is which. And just briefly looking at my graphs, I can see the first three, 1, 2, and 3, have curved position time graphs. When I see a curve in the position time, that indicates that its slope is changing. And since the slope is the velocity, the slope on the position time graph is equal to the value of the velocity, and that slope is changing, that means that the velocity is changing. And if the velocity is changing, that means I have a non-zero acceleration. So in graphs 1, 2, and 3, I have a curved position time graph indicating my velocity is changing, therefore indicating that I have some non-zero acceleration. If I go down to my graphs, equipment setups rather, below, I can see that there are only 3 equipment setups that have a golden arrow indicating acceleration. So of those 3 right there, I know those 3 right below my 3 curved graphs, those 3 equipment setups, the only ones with the golden arrow are the only ones with a non-zero acceleration, and therefore it has to be A, B, and C must match up with 1, 2, and 3 somehow. Graphs 4 and 5 have a linear function for my position time, where it's a straight line where the slope is constant, meaning the value of the velocity is a constant number, and therefore has 0 acceleration. We saw that before in our dot diagram lab when we dropped clay spheres down onto the ground, and at a constant speed or constant velocity we got a linear graph for our position versus time. The equipment setups D and E correspond to position time graphs that are linear. Since D and E are not on an incline, they just have a 0 acceleration and some constant velocity. We can see that they're indicated, equipment setups D and E, with just a black arrow indicating the direction of their velocity and no golden arrow indicating no acceleration. Also, we can tell that this should be the case, since if they're on a nearly frictionless track that has 0 incline, then given some initial push or some beginning force to get them moving, they should move at such a constant velocity without any additional increase or decrease in speed, since they're not in an angle for gravity to accelerate them or decelerate them. I can correspond 4 and 5 with D and E quite easily by saying, look, 4 must be moving in the negative direction, since its position time graph shows a change in position that is in the negative direction towards the 0 line, going from positive to negative, and graph 5 shows a change in position that is in the positive direction, going from 0 to a larger magnitude positive position number. Since we said away from the graph was positive, or away from the motion detector rather, was positive direction, and towards the motion detector was the negative direction, then we can say that E must go with graph number 5, and D must go with graph number 4. Going back to my graphs 1, 2, and 3, I can see that 1 and 3 are very similar, those position time graphs, except that 1 has a faster rate and change of the slope. So if I draw in my slopes, just kind of estimate them in green here, it starts off with the very low magnitude slope, which indicates a low velocity. all the while that slope is positive, so the velocity is positive the whole time. It's increasing in magnitude. The change in position of my cart's in the positive direction. My v is increasing and is positive the whole time, which means I must also have a positive acceleration. The sign of the positive, or the sign of the acceleration and the velocity, if they are the same, must indicate a speeding up. If their signs or directions are opposite, say if velocity is positive and acceleration is negative, then that indicates the object is slowing down. So here we have 1 and 3 again, very similar, except how quickly the slope is changing is different. For 1, it must have graph 1, it must have a greater acceleration. It's increasing in its velocity at a faster rate. Otherwise, the graphs are pretty much the same. Both objects are moving in the positive direction, their velocities are increasing, and they have some positive acceleration. If I look down at my equipment setups A, B, and C, the remaining setups that I have to match, I can see that the angle of incline for A, call it theta here at some angle, is smaller than the angle of incline over here for equipment setup B, call it theta B, theta A. When I have a larger angle of incline, I have a greater acceleration. Imagine that I have a dynamics track that is set up all the way up here at 90 degrees angle. With a 90-degree angle, the acceleration is going to be just the same acceleration we have in free fall, 9.80 meters per second squared downward. So as I increase the angle, my red angle theta, as I increase that, the magnitude of my acceleration gets larger. Here's my acceleration right there with my golden arrow, and I have a smaller golden arrow vector indicating the smaller acceleration here with that equipment setup. So both of these objects in setups A and B, both carts, are going to be moving in the positive direction. They're both going to be speeding up, and they're both going to have a magnitude of their velocity that is the whole time positive, but the whole time also increasing, as depicted by the increasing slopes on graphs 1 and 3. But because B has a larger angle, and therefore a greater incline, it'll also have a greater acceleration, and it should have a sharper curve with a more quickly increasing rate and change of the slope. So graph number 1 must match with setup B, and graph number 3 must match with setup lettered A. By elimination, that leaves equipment setup C with graph 2, and we can examine why that must be the case. Notice that in graph number 2, I have a beginning with a very steep negative slope that decreases in magnitude towards 0 slope, where velocity is 0 right here, since the slope on my position time graph is equal to the velocity. I reach 0 velocity and then have a change in the direction of my slope. It's a positive slope all the way up here, increasing in magnitude. So here I have a positive velocity increasing in magnitude. Here I have a negative velocity that is decreasing in magnitude. So I have a slowing down, moving in the negative direction, and then I have a speeding up, moving in the positive direction. And at some point in between, I come to a stop. So we can see that on this equipment setup C, I have an acceleration that is opposite to my velocity, so I should have a slowing down on this first portion of the trip while the cart is moving up the ramp. It has been given some initial velocity, some initial push maybe to give it that velocity upwards, up the ramp in the negative direction. So there's the first half of our graph number 2. We have a negative direction of the particle of the cart slowing down. It reaches some 0 velocity right here in front of the motion detector, and then it starts to speed up coming back down the ramp, and we see that speeding up and movement in the positive direction in the second half of graph number 2. So graph number 2 much match with C. We already did the last two over there. Graphs 4 and 5 match with the D and E. There are many opportunities on the AP exam to take a look at problems and go step by step through each part and try to get as detailed as possible in the solutions, but often it is much quicker and more efficient to simply do some elimination of possible answers to get at what the correct ones should be. So a technique for this one is to look at all of those graphs at once and say, look, 1 and 3 are similar, but one has a greater rate and change of the slope. They're both moving in the positive direction, they're both speeding up, but one's speeding up more quickly, so it must have a greater acceleration. So which one of my setups looks similar, but has a greater acceleration. That's going to be the one with the greater angle. So that gives me that difference between setups A and B coordinating to graphs 1 and 3. I then have that graph number 2, which indicates first a slowing down and then a speeding up. And so I can see that that's going to have to be a cart that's pushed up against the direction that gravity wants the cart to move, so that the cart is slowing down on its way up and then speeding up on its way down. Then for the last two graphs, I know that 4 and 5, they're linear, so they have to be ones with zero acceleration. I only have two setups that give me that, and the difference just is a matter of looking at the direction. Is very easy. One is moving in the negative direction, that has to be towards the detector, and the other is moving in the positive direction, that has to be moving away from the detector. So there's a real quick way, just out of elimination, to kind of go through and match up those graphs.